Okay, so I just want to take a minute and review what we talked about in 9.2b, and that is how to find the sum of the first 125 terms of the following sequence. So the first thing we need to do is remember the formula for finding that without using a full summation on our calculator, and that formula is the number of terms divided by 2 times our first term, which happens to be 7 in this case, plus the very last term, that 125th term. So to be able to find that 125th term, we have to be able to find the nth term. So the formula that allows me to find any term in that sequence. So to do that, we need to know several things. First thing we need to know is what is the common difference in our sequence. So I look, and each time I am adding 3, so my common difference is 3. And then we have to find our 0 term. So my first term was 7. So if I work backwards, I take that first term and I subtract the difference. I get my 0 term, which would be 4, which kind of makes sense. 4, go up by 3, go up by 3, and I get each number from here. So this will allow me to find my nth term. So any term, n, can be found by my difference times n plus 4. So now, if I want to find that 125th term, so I can figure out what all those terms add up to, I'm just going to go ahead and plug in 125 in for n. So this will be 3 times 125 plus 4. So 3 times 125 plus 4. And we get 379. So this is the number we're plugging in up here. And now we can actually figure out what that sum would be. So our sum is going to be 62.5 times 386 and that tells us that all 125 terms, all of the first 125 terms in the sequence would add up to be 24,125. Okay, and so that's what we talked about in 9.2b. So now we're going to move on to 9.3. And 9.3 is a new type of sequence called a geometric sequence. And what's interesting about a geometric sequence, where our arithmetic sequence before was linear. We added the same number each time. Our equation was a linear equation, kind of like a y equals mx plus b idea. With a geometric sequence, consecutive terms have a common ratio. And so what ends up happening with this geometric sequence is instead of adding the same number each time, we multiply it by the same number each time. So here I would times by 2. Here I would times by 2. Here I would times by 2. And that is our common ratio. Now, sometimes when we have two terms, we don't know what that common ratio would be, and we can actually figure that out. So this one was easy. I could look and I could see that I just times by 2. But what if I had like 2/3 and 2/3 and then 2/6 and then 2/12, so on and so forth. Sorry, it was hard to come up with something just off the top of my head. But you weren't really sure what was happening. Then what you can do is you can take any term, so let's say this one, 2/6, and you could divide by the previous term. So I would divide by 2/3. Which really means I'm going to take that 2/6 and I'm going to times by the reciprocal 3/2. And so that allows me to have a 3/6, which means that my common ratio is 1/2. And so that's just something we can use to help us figure out what R is, in case we can't tell just by looking at it. Okay, so now we're going to look at some sequences and we're going to determine, are they geometric? And then if they're geometric, we have to determine what the common ratio is. So on our first one, it looks like, looks like I could times by 2 each time. So yes, this is geometric, and we times by 2, so that means our r is 2. Okay, on our next one, it looks like we can times by 3. So yes, this is geometric, and our r would be 3. And then our next one, looks like we're squaring each time. 1 times 4, 4 times, no, that doesn't work. So this is not geometric. Okay, and our next one, it looks like we alternate between positive and negative, and then we times by 3 on the bottom. So yes, our common ratio would be -1/3. And again, if you were unsure, we could actually check. So let's take our 1/9 and divide by the previous term, -1/3. So instead of dividing, I times by the reciprocal, which gives me 3 over -9, which is -1/3. And so see how that just kind of matches there. Now what I want to talk about is we have the nth term written on here because I wanted to point out something. Notice how our common ratio here is 2, but that also pops up there on our nth term. Our common ratio here was 3, and it pops up right there on our nth term. Here our common ratio was -1/3, and look where it pops up. And so now look at all of these. They're not linear, but they are exponential in nature. So because they're exponential in nature, that gives us an idea of how we're going to write our nth term for our geometric sequences. Our common ratio is going to be the base, and then we're going to have something dealing with our n for our exponent. So how do we find the nth term? Well, here's our formula. A to the nth term of any geometric sequence is going to be the first term times our common ratio raised to the n-1 power. So we're going to work on that now on some problems. So find the first 5 terms of the geometric sequence whose first term is a1 equals 2 and our common ratio r equals 3. So we have several things that we can do here. We can just go ahead and say, hey, my first number, or my first term, is 2. And then since my common ratio is 3, I can just keep timesing by 3. So 2 times 3 gives me 6. 6 times 3 gives me 18. 18 times 3 gives me 54. 54 times 3 gives me 162. And there's my first 5 terms. But if I wanted to know what's the 125th term in here, we'd have to go ahead and find the nth term. So we're going to use that idea of any term, like my 125th term, can be found by my first term, 2, times my common ratio. So each time I timesed by 3. So this is going to be 3 to the n-1 power. And then we can double check that to make sure that that works. So if I plug in 5 here for my 5th term, 2 times 3 to the 5 minus 1. So 2 times 3 to the 4th. So let's calculate 3 to the 4th. That's 81, and then times by 2 gives me 162. So that works, because I just plugged in that 5, and it gave me the correct 5th term. So let's go ahead and try another one. Find the 15th term of the geometric sequence whose first term is 20 and r is 1.05. So we can do our nth term. So an is my first term, 20, times my r to the n-1 power. And then from here, we want to find the 15th term. So we're going to go ahead and do a sub 15 would be 20 times 1.05 to the 15 minus 1 power, so the 14th power. And then on my calculator, I'm going to go ahead and type in 1.05 to the 14th power. And then I'm going to times that by 20. And so then, because this is a really long decimal and I'm going to round, I'm going to go ahead and say my 15th term is approximately 39.599. So I'm using that 3 decimal place rounding idea, but also saying that this is not my exact 15th term, but it's approximately the 15th term. Okay, so on our next problem, find the nth term of the geometric sequence, and then what's the 9th term of the sequence. So now that we have a sequence, we're going to have to look and see, okay, what do I times by each time? And it looks like I times by 3. So our r is 3. Our first term is 5, so now we can write our nth term is my first term times 3 to the n minus 1 power. And now if I want to find that 9th term, I'll just go ahead and plug in 9 for n. So my 9th term would be 5 times 3 to the 9 minus 1, which is 8. And then I'm going to go ahead and calculate 3 to the 8th power, and then times by 5. So my 9th term should be 32,805. So now we're going to get a little bit more complicated, because now we're going to be given our 4th term and then our 10th term. So what we can do is we can take the bigger term, so my 10th term, and I can set that equal to my 4th term times r to the 10 minus 4. Why does that work? So if I think about my sequence, I've got my first, second, third, 4th term, and then my 5th and 6th and 7th and so on and so forth. So what ends up happening is that if this is my 4th term, I have to times that by r to get the 5th, and then times by r to get the 6th, and times by r to get the 7th, and so on and so forth. And I'm going to keep doing this until I get to my 10th one, which means that I have to times by r 6 times until I can get that 10th term. And that's how we set that up. My 10th term is going to be the 4th term times r 6 more times. Now I don't know what r is, but this will allow me to calculate r. So now that I have that set up, I can go ahead and work with calculating r. So the first thing I have to do is get r by itself. So I get rid of this 125 on this side. But if I divide by 125 on this side, I have to divide by 125 on this side. So that means I'm really just going to put it on the bottom of the fraction, and those cancel out. Then over here, these will cancel out, which leaves me with something over 64. And don't forget that if this cancels out, 125 divided by 125 is really the number 1. So it leaves me with a 1 on top. So I have 1 over 64 equals r to the 6th power. And then I'd want to figure out, well, how do I undo the 6th power? Well, I could 6th root both sides. And if you don't know how to do that on your calculator, this is what I typically do, because back when I was able to do this in when I had to do this in high school, not able to do this, well, I was. I couldn't 6th root stuff. My calculator didn't allow me that ability. So we used the idea that instead of the 6th root, we did the 1/6 power. Because now 6 times 1/6 gives me 1, so this is really r to the 1st power. And then this is something I can type into my calculator. I can actually put in parentheses 1 divided by 64, end parentheses, to the 1/6 power. And when I do the 1/6 power, my calculator I have to do to the power parentheses 1 divided by 6. But it tells me my answer. It tells me that r is 0.5. which now we've got to kind of work backwards or forwards. So now I could do 0.25 or 125 times 0.5. So 125 times 0.5 gives me 62.5. But what they did is they had it as fractions. So I'm really going to want to make my r, instead of 0.5, 1/2. So half of 125 is 125 over 2. Half of that is going to be 125 over 4. Half of that is going to be 125 over 8. And so that allows me to keep going. So if I zoom ahead in my sequence to, here's my 10th, 11th, 12th, 10th, 11th, 12th, 13th, 14th term, then I can say, okay, this is 125 over 64, and then times by 1/2. 125 over what's 64 times 2? 128. And then 125 times by 2, 256. And then 125 over times by 2 again, 512. And then times by 2 again. So this is going to be 125 over 1024. So kind of looking at how that pattern's going back. What happens if you wanted to find the nth term? If you wanted to find the nth term, instead of timesing by 1/2 each time to move forward, I can divide by 1/2 to move backwards. And remember how I had said before that instead of dividing by a fraction, I can times by the reciprocal. So I can times by the flipped version of that. So to move backwards, I can times by 2. So 125 times 2 gives me 250. 250 times 2 gives me 500. 500 times 2 gives me 1,000. And that gives me my first term, which then allows me to write my nth term. So if I wanted to go that way, I could say, okay, my first term is 1,000. My r is 1/2. And then it should be the power of n minus 1. And then we could use that to find the 14th term or the 13th term or any term from there. So again, multiple options for you. I know this looks crazy, but again, each mind thinks differently, and so you can go about it differently and still get the correct answer. Okay, so let's try another one. We have find A10 if A2 is 3 and A5 is 3 over 64. So I'm going to take my higher term, the 5th term. So 3 over 64 would be equal to my smaller term, the second one, times r to the, and then I have to figure out how many times I have to go from the second term to the 5th term. So I'm going to have to go 3 terms, so that's 3 r's that I'm multiplying. So now that I have that set up, I'm going to go ahead and divide by 3 on both sides, which means this will cancel, that'll cancel. So now I have 1 over 64, which looks familiar, equals this time r to the 3rd. So now I want to do the 3rd power, undo that. So I'm going to do the 1/3 power on both sides. So this becomes r to the 1st equals 1/4. So now I'm going to go ahead and do the nth term. So my nth term is going to be my first term times my r. So my r is 1/4 to the n minus 1 power. So I've got to figure out what that first term is to plug in there. So now I'm going to go back to the idea that, well, here's my first term, here's my second term, and my second term was 3. So if I'm going to move forward, I'm going to times by 1/4. But if I want to move backwards, I want to divide by 1/4. And the opposite of dividing by 1/4 is timesing by the reciprocal. So I times by 4 to move backwards, and I get my first term of 12. So this 12 will go right here. And now I can use that to find my 10th term. So a of 10 is going to be 12 times 1/4 to the 9th power. So a10 is really going to be 12 times 1/4 to the 9th. And so we can work it out this way. Or we could actually do 1/4, so 0.25 to the 9th, and then times by 12. I'm doing it this way because I noticed that this can be divided by 4, and this can be divided by 4 to give me 4 to the 8th power, which now gives me a pretty decent fraction, 3/4 to the 8th power, and then I can just calculate 4 to the 8th. So 3/65,536. Why do I show it to you this way? Because I believe in the back of the textbook, they're showing it to you in fractions because we're in precalc. We should be able to work with fractions by now. But if you did not want to, and you want to take the lazy man's way out, we can do 0.25 to the 9th power, and then times by 12. And we're going to get a10 is approximately, because again this is a decimal, 4.5776. And then at the end it says e to the -5, which means it's times 10 to the -5 power, which means that it's approximately 0.12345 And so again, either answer is truly appropriate as long as you're going about the right way of calculating it. Okay, so again, find the nth term of the geometric sequence. So my nth term will be my first one times my common ratio, and then n minus 1 power. And then we want to find the 8th term. So my 8th term would be 5 times 3/2 to the 8 minus 1, which is 7. And so again, you can calculate fraction-wise. So I could do 3 to the 7th power, and I could do 2 to the 7th power. So I get 5 times 2187 over 128. So this is 10,935 over 128. Or I can go decimal wise. I could do 5 times 1.5 to the 7th power. So 1.5 to the 7th. And then times by 5, which gives me an approximately 85.4297. So again, options, but you're going to find that if you're going to go farther in mathematics, you want to practice working those out with those fractions. Okay, write the first 5 terms of the geometric sequence, determine r, and write the nth terms of the sequence. So why do we have this? Because we have this little thing here that we don't talk a lot about, but we do a little, and so sometimes people look at that and they're like, what does this mean? So I wanted to talk about it one more time. We have 8, the first power is 81, so my first term is 81. And this tells me that any term I want is going to be 1/3 times the previous term. And so that's why we have a k plus 1 here and a k here. So to find the 1 after k, I'm going to do 1/3 times the previous term. So from here, if I want to find my next term, I'm going to do 1/3 of 81. And that's going to give me 27. And then 1/3 of 27, and that's going to give me 9. And 1/3 of 9 is going to give me 3. And 1/3 of 3 is going to give me 1. And so this really kind of actually tells me what to do to find each next term. It's called the recursive rule, because I can use this one with the rule to help me find this one. And I use this one to help me find that one, so on and so forth. But if I want to find an nth term, I have to actually figure out what am I doing each time. But luckily, this recursive idea tells me right away, I am multiplying by 1/3 each time. So I take my first term, multiply by 1/3 to the n minus 1 power. And that gives us that nth term. Is my board going to work? There we go. So now we're going to go into the last part of 9.3 and the sum of a finite geometric sequence. So this is our rule for that. So if I wanted to find the sum of this sequence right here, I know it's finite because I'm adding up until the 12th term. I know my r is the base of my exponential function, and my a1 is the number in front, because that's my rule for the geometric sequence. So now if I want to find the sum of this, because for some reason I don't have one of the newer calculators that allows me to calculate sums, or if I just forgot where to find that idea, I can use this rule. So my sum of my 12 terms of the geometric sequence would be equal to my very first term. Oh, that's not my first term. Why is it not my first term? Because my first term is when I plug in n equals 1. So when I plug in n equals 1, it'd be 4 times 0.3 to the first power, which is, sorry about that freak out there, which is 1.2. Why did I think? Because we were used to doing this. A times n equals a to the 1 times r to the n minus 1. So I was thinking about that, but the problem is this didn't match with that. So that means that this can't be my first term. My first term is really 1.2. So it's going to be 1.2 times 1 minus my r, so that r is 0.3, to the nth power, so this number is my n, 12, over 1 minus 0.3. So when I'm going to calculate this, the first thing I'm going to do is I'm going to do 0.3 to the 12th power, and then I'm going to subtract that from 1. So it's going to give me an interesting decimal, 0.999. There's a lot of them. I think there's 6. And then I'm going to divide by the 1 minus 0.3, which is 0.7. Now you don't want to round this decimal here and keep rounding throughout your stuff, because the more rounding you do, the more errors you make. So keeping the full value in your calculator while you're calculating is going to be very helpful. So I take this number that's already in my calculator, I'm going to divide by that 0.7, and then I'm going to take that answer, I'm going to times by 1.2, and it gives me an approximate value of 1.71428, so on and so forth. Okay, so we're going to try another one. So we're going to find the sum of our 7 terms, our first 7 terms of the geometric sequence. And our first term is when we plug in 1 into there, because that's where we're starting our sequence. So this is going to be negative 4 to the 1 minus 1. So that's going to give us negative 4 to the 0 power. And we've talked about that, how anything to the 0 power is really just 1. So my first term is 1 times 1 minus my r. So the base of my exponential function is my r. So this is going to be negative 4 to that nth power, so the 7th power, over 1 minus my r. And so this will tell us the sum of the first 7 terms. So I'm going to start by doing -4 to the 7th power. And I'm going to do 1 minus that answer. So I get 1 times 16,385 over 1 minus -4, add a line, change the sign, we get 5. So really it's just that 16,385 divided by 5, which means these should add up to 3,277. Okay. Infinite geometric series. So a finite series is nice because you only have so many terms. But if my terms get bigger and bigger and bigger and bigger in an infinite series, it's just going to keep approaching infinity. So those numbers are going to approach infinity, the sum's going to approach infinity, but if my numbers get smaller and smaller and smaller and smaller and smaller, then it's actually going to approach a certain value. And so we can tell that if our r is less than 1, like 1/2, 1/5, 2/3, 3/4, but less than 1, then it's going to actually approach a certain number. And that number is going to be our first term divided by 1 minus r. So, for example, we have the summation of n equals 1 to infinity of 4 times 0.6 to the n minus 1 power. Now, I know this is going to actually converge to a number because this r is less than 1. So what I can do is I could find my first term. So I'm going to plug in n equals 1. So 4 times 0.6 to the 1 minus 1. So this 0.6 to the 0 power, which really just tells me that this is going to be 4. My first term is 4. And so my sum of the series is going to be the first term divided by 1 minus my r, 0.6. So this is going to be 4 divided by 0.4, which is going to give us 10. So as I add more and more and more terms into that, it's going to get closer and closer and closer to the number 10. So if I keep going for infinity, it's going to give me that number. And so on our next one, we kind of have the same idea. Now, we could probably look at this and tell what the answer would be, but what if we were given this and we were trying to figure out, well, what is our common ratio? I know my first term is 3, but what's my r? And so if you don't know, what you can do is you can pick any term, and I could divide by that previous term, and it'll tell me what that common ratio is. So this is my r, which now allows me to figure out what our sum would be. Our sum would be our first term divided by 1 minus our r. So this is 3 divided by 0.9, which actually becomes I should have known that. 3.33333. And when we think about it, yeah, this is 3, and then I added on a 0.3, and then I added on a 0.03, and then a 0.003. And as I keep going, I keep just adding on another 3 at the end. So it really tells us something that we could have saw just by looking at it. We could have figured out just by looking at it. But if we couldn't tell just by looking at it, what's the way we could go about doing that? Okay, so 2 more, the same idea. This one's a finite. This one is not. So we're going to go ahead and do the finite one first. The first thing we need to do is figure out our first term. So my first term would be 16 times 1/2 to the first power. So half of 16 gives me 8. And then the sum of my first 10 terms would be my first term times 1 minus my ratio, which is 1/2, to the 10th power, because that's my n, over 1 minus my ratio. And so again, we could go about this several ways. We could go about this using decimals or fractions. I'm going to go ahead and use decimals just for time's sake. So 0.5 to the 10th power, and then 1 minus that. And then 1 minus 1/2 is 1/2. So I'm going to take that top number and divide by 1/2, or 0.5, which means I'm going to have 8 times 1.998, so on and so forth, which means the sum of my first 10 terms would be 15.984375, so on. And again, you can go about that using fractions, but we're just trying to save some time here. So in our infinite one, very similar nature. We're starting with a 0 instead of a 1 on this one, but that's okay. Very similar in nature. Our first term, we'd have to find out. So 16 times 1/2 to the 0 power. And so that means it's just 16 times 1, so 16. And then my sum should be 16 divided by 1 minus our r, so our 1/2. So this becomes 16 divided by 1/2, or I can times by the reciprocal, times by 2 over 1, which gives me 32. Okay, so your assignment due next time we have class is 9.3, number 1 through 41 odd, 55, 57, 67, and 71.